Okay, we're recording. Is something actually worth taking a picture of there?
Yeah, it was to the girls that ditched me in this class.
Oh, okay. Yeah, there were a few of those. Yeah. So, well, you're missing out. Okay. Well, yeah, because we had 19 people last time. Well, and some grad students did too. So, yeah.
So we have 10 people this time?
Yes.
Including
Mr.
Dr.
Yeah. 1, 2, 3, 4, 6. Yeah, including him. So.
Why does he like compares to professor?
What is his name?
Dr. Zhu, Zhou.
Right.
I don't. It's kind of weird because he originally wanted to apply for a PhD program, but faculty at USM cannot take a doctoral program at USM. Yeah, this is a rule against it. And yet they are allowed to join a master's program.
That's kind of weird.
Yeah, and I'm not sure what purpose the master's serves on top of his existing PhD. So I've never asked him, so I'm not his advisor anyway. So. Okay, anyhow, welcome to Math 461, Numerical 2, yay. So, get all the junk out of the way. Syllabus, handouts, all that stuff. So, okay, syllabus and a schedule. Okay. Of course, I'm going to be making all these references to, it's like last semester, except that doesn't really help you very much, Sarah. But yeah. I'll try to take that into account. Okay. But as far as format of the class, yeah, it is pretty much like last semester. Maybe I should stand in front of a camera. So, okay. So that's for coursework. There'll be homeworks that'll be roughly weekly, taken from the textbook. That's the textbook from last semester, first course in Numerical Methods by Asher and Greif. Now, of course, you all have a book from last semester, except you don't. I'll hook you up. Okay. All right. Then I do count attendance, like last time, and I can see that everybody who can be here is here. So that's working. One slight difference is about the final exam. So you all suffered through the oral final last time, and we have that again. However, for this class, I'm actually giving you more of a choice. Instead of the oral final, I have another alternative for final that's like a final project that's straight coding and pretty involved too. So I would only recommend it for coding enthusiasts like Vivian. That deals with some of the methods that I'm covering towards the end. So for solving certain differential equations or systems of equations. So it's not for the faint of heart coding wise. So if you'd rather do that, then the oral final. And last time I offered this, there were a couple students who actually chose that option. So that's something to contemplate. Okay, but other than that, there's really no difference from last time. Let's see. Now as you can see on the schedule that I gave out, so it's reading from either the textbook, Asher and Greif, which is once again where I'll be drawing homework problems from, so that part's not going to change. And also my notes. So if you go to the course website, so now instead of going to matthusn.edu/Lambert/math460, you'll go to 461. If you go to, so to get the notes, just like before, you go to the resources page, and then there'll be a link there to the textbook that I'm working on with Amber Sumner, Explorations in Numerical Analysis, and it is password protected. Password is the same as last time, except I've updated the course number. So MAT 461 ENA for title, Explorations in Numerical Analysis. And the old link for 460, that's still up. But I'd still use this one because as I update the notes, this is the only one I'm going to be updating. So keep that in mind. Okay, so you can follow along in the notes or in Asher and Bright. Okay, now, so what I'll do today is making sure this is still taping, because if it stops, that's really going to bug me. Okay. So since I wasn't recording this class last semester, what I'm going to do with the videos is, because I also do this in my other class, 606, that meets the next period. And as soon as both classes are over, I work right away on getting these uploaded to YouTube. If you want, if you miss a class and you want to see the videos later, I will post them on the lectures page. And I try to have them up ASAP. But once they're on YouTube, the quality is not quite what I would like, so I'd have YouTube do a little enhancing on them, and that could take some time. But anyway, certainly by the evening of class, they're up and ready to view. So I'll go ahead and so just watch for the links that I post here each day to get those. Now, just like last semester, there'll be certain labs. Usually, let's see. I guess often labs are on Wednesdays. There might be an occasional one that's on a Monday instead. I'll let you know when labs come up. We're downstairs in 205. I'm not sure how we'll go with recording the labs. I haven't done that yet. I'll try it, and we'll see how that goes.
I think there's a software you can actually record your screen.
Oh yeah, there is. But yeah, I'd certainly rather do that than recording like this for the lecture. So whether it's reliable or not is.
We used it a couple of times. It's like old
Yeah.
beta versions.
Yeah. Well, we can play around with that with the first lab. So yeah, good thing you mentioned that.
Also, the labs are not as frequent.
Yeah, there aren't as many of them just because there's a lot of stuff to cover, and so another thing that's going to come up is I'm going to give it today. I'm going to give an overview of the general topics that I'll be covering, and if there's time left over, I'll jump into the first one. But if you look at the schedule, the first part of the course is on methods for solving initial value problems, ODEs. And what's interesting is Math 285, the differential equations first class, is a prerequisite for this, except you don't really need to know much about differential equations from that class to be able to understand numerical methods for this class. All the stuff you learned back then about method of undetermined coefficients, variation of parameters, we're not doing any of that. So if you've forgotten it, that's okay. So that'll be the first third or so of the course up until getting into the second half of February. And then we get into numerical linear algebra. And actually, Amber Sumner is going to take over and teach that portion of the class because among the graduate students, she's our numerical linear algebra person. I'll still be around. And actually, I guess after spring break, she will be away at a conference, so I'll take over again at that point. And then we get into other things like solving systems of nonlinear equations. Because last semester we did one equation, like using Newton's method, which most of you took the take-home oral final on. But now it's systems of equations, and then boundary value problems for differential equations. So that'll occupy the last third, and then the final programming project will be on that. So, okay. So, but yeah, it's unfortunate that we only have a little more than, well, actually, we have a little less than half of 460 people continue on into 461, and then Sarah has joined us after a semester in Peru. So, so I guess you're a guinea pig. Let's see how it goes taking 461 without having taken 460. But okay, but I know you have to.
Peru, they eat guinea pig, just saying.
Yeah, I was just thinking about that. I was like, they eat guinea pig in Peru.
What?
They eat guinea pig in Peru.
So, sorry, what?
They eat guinea pig
Oh.
in
Yeah,
Peru.
it's a delicacy.
Okay.
So,
Well, that's a good
don't
thing.
call me a guinea pig.
Yes, but you're not there anymore, so
That's true.
you're safe.
She escaped.
Yeah, it's good.
You cannibal.
It's little bacon. It's guinea bacon.
Okay, well, there's something new every day. Oh, fine. Okay, so now I can get into overview of the topics. Okay. Just to give you guys a bit of a preview of what's coming. Okay. Oh, that's right. We didn't do what we did last semester. We had the books underneath. But it might not be necessary. Actually, we'll see how it looks. Yeah, because I didn't even think about it. It's like why do we need so much last time? But yeah, that would make it easier because then you can sit wherever you want. Okay. Let's line this up. Okay. Yeah, so that's why I need these front tables. Not for that, but fortunately we don't have too many people here anyway. Okay. All right. Okay. Now, so the same criteria for numerical methods. So what this course is about is the same general theme, same considerations, just we're looking at different problems than before. So this course, as 460 was, is about designing numerical methods for computing approximate solutions. And for this semester, we've drawn problems from differential equations and linear algebra. That's our focus this time. And although in this semester we get into ordinary differential equations, as far as we're going to get, several of you are taking partial differential equations, and a lot of the ideas from these numerical methods can be applied in that setting. Okay, so we have the same criteria for designing good methods. This is a review of some important ideas from last semester. Of course, the method should be accurate. Really, no elaboration needed there. Unfortunately, to stop short of an exact solution. We're solving a lot of problems for which no exact solution is even available. Now, for solving systems of linear equations, the linear algebra portion, we're talking about problems that can be solved exactly, but are such solution methods doing by hand efficient? That may be completely impractical. So again, we need to see what can be done that still maintains accuracy, but also we must have methods that are efficient. So the key is idea of computing time is needs to be thought of as a finite and expensive resource. And that's literally true. Computers cost a lot to run and maintain. So if you're going to have solution methods that take far more time than they need to, then that really is wasteful. And then the one that's thought about that's not as obvious, but turns out to be quite important. Methods need to be robust, because what can happen is you can have a method that is efficient, that is accurate, but maybe for certain problems might give you a solution that is not as accurate as might be otherwise. Maybe you can't really trust the solutions that you get. This is particularly troublesome with the linear algebra portion of a course. When we're getting to solving systems of linear equations, we get into what is called conditioning. I mentioned last semester it came up, problems could be well-conditioned or ill-conditioned. So you may have a situation where you have a system of linear equations, you go ahead and solve it in the usual way, but you might tweak the system, like the matrix or the right-hand side values, just a tiny amount, and it throws off a solution by a lot. And that's something that we have to be very careful about. Because just because a method is normally reliable, turns out a solution in a reasonable amount of time, doesn't mean that it is anywhere near the right answer, depending on the method that you use. So all three of these come together to make a reliable numerical method that you'd actually put in commercial software. All right, so now I'm going to say a little something about the types of problems and a little bit about the types of methods we'll be using to solve them. That's on tap for this semester. Okay, so as I mentioned before, first you're going to spend a lot of time on initial value problems for ODE, so ordinary differential equations. So we have a general first order ODE. dy dt is equal to some function f that depends on t and y. Y is your solution. And you have an initial condition, which I'll abbreviate as IC. So solution at some initial time is equal to some initial value. Now, in a course like Math 285, you dealt with this kind of problem in the first part of the course, likely from Dr. Ding. And so you learn certain methods for certain special cases, like is it an exact equation? Is it a linear equation? Is it separable? And you had solution techniques specialized to those cases. And if a problem did not fall into one of those special cases, then it's like, well, I don't know what to do. You're out of luck. This is, here with numerical methods, it's the opposite philosophy. That we are never going to care what this time derivative function f is. We're just going to design numerical methods that will be able to solve this computer product solution to this problem, whether f falls into some special category or not. So it's very freeing in that sense that you're not that you can solve a much wider variety of problems, which is the beauty of numerical methods in general. We're just settling for approximate solutions, but these approximate solutions can be so accurate that, for all practical purposes, it really is like an exact solution. Okay, so what do these numerical methods actually produce? So that's one big difference in settling for an approximate solution. Because when you solve these problems in a differential equations course, you would come up with an actual function, a formula for y of t that satisfies the ODE and the initial conditions. So the output is, instead of y of t equals some function of t, you compute y values, or call them y1, y2, y3, and so on, where each y value is an approximation of a solution at a corresponding t value. And each of these t values would be your initial time t naught plus some multiple of a time step, delta t. So you're going to start at the initial time t naught and just march forward in time and compute approximate solution values. And as you can imagine, the smaller time steps you take, delta t, the more accurate your solution is going to be. But how much more accurate? That's one of the things that we need to take a look at. All right. As far as there are different classes of methods that we'll take a look at. There's various ways of classifying them. Okay. First kind of method we'll look at is called a one-step method. And what that means is you're basically using information about the solution at time n to compute your solution at time n plus 1. You are not using any other information from earlier in time. So a lot of the simplest methods come about this way, using this one-step approach, as opposed to multi-step methods, where you are reaching back S steps, where S is something of your choosing. So you're using older information. Okay. So that's another whole category of methods. So sometimes if you're taking more information, because you can think of it as you're basically extrapolating. You're seeing what happened at this time to figure out what's happening at the next time. If you use more historical information, your extrapolation arguably is more accurate, and that's the virtue of multi-step methods. They can take this information into account in a very efficient way. Now, one thing that's going to be interesting though when we design multi-step methods is we're going to use some topics from last semester of polynomial interpolation and numerical differentiation and integration. And we're going to do something that, in terms of the ideas from 460, seem really strange. Because if you're numerically integrating a function from AB, you're going to think, oh, well, you should use interpolation points in AB. But not in this case. We're actually going to integrate over a certain interval using points outside of that interval. And believe it or not, it's going to make perfect sense to do so. Okay, so that's one way of breaking down methods, time-stepping methods into categories. Another way of categorizing methods is either explicit methods. My favorite definition, I guess most intuitive definition of explicit methods is that you can obtain your solution at the new time by, as students often like to say, plug and chug. That you're just substituting values into various functions and just grinding it out and you get a solution. Now, it may not be as clear as I want it to be until I contrast this with the other kind of time-stepping method, implicit methods, where you have to solve some sort of equation to get your new solution value at time n plus 1 from the previous values at time n minus 1, and so forth. And the thing is, that equation might be a nonlinear equation, such as the ones you used Newton's method on last semester. Or maybe you're solving a system of differential equations, therefore you must solve a system of equations every single time you take a time step. So that can be a lot of work. But the thing is, it seems like this would be so much more expensive than this. And in many cases it is. Except what if you were able to take fewer steps in time than you would using an explicit method? Then it's actually justified. So that's something to keep in mind, that it's not just how much work you're doing per time step, it's the overall amount of work to get from your initial time all the way to your final time using however many steps. We have to take a look at that to see what is the best approach. Okay. All right. Now, okay. Now, certain issues that come up when solving differential equations, and we'll spend a fair amount of time on these, because every problem has its pitfalls that you have to be concerned about, as we saw last semester. One is stability. Any time-stepping method we see, whether it's one-step, multi-step, explicit, implicit, we need to make sure that it's stable for the problem that we're trying it out on. Generally what that means is you have to make sure that your time step, your delta t, is small enough in order to get the correct behavior of a solution. Because it's kind of like a Goldilocks problem in a way. You don't want to choose delta t to be too small because that's a lot of computational expense. But you also don't want to choose it too large, because then you're going to lose, not only are you going to lose accuracy, but your solution may behave in a totally non-physical way. Like for instance, if you're solving a differential equation where the solution is supposed to decay to 0 over time, but maybe you choose delta t too large and your solution doesn't decay at all. Maybe it blows up, maybe it exponentially grows. So if you're not careful, that's what can happen. That your solution is so far off it just doesn't even make any sense. So stability is what this is about, to make sure we get that reasonable behavior. And another problem is that goes hand in hand with stability, and one that I spend a lot of time on in my own research program, and any of you who work with me are familiar with this already, stiffness. And this is what comes about when you have to choose delta t much smaller than is necessary in order to represent the solution. So what I mean by that is, so suppose your solution, your exact solution, is a very smooth function. Maybe it decays to 0 as t increases. So in order to represent that kind of function accurately, you would only need to evaluate it every so often. So you may not need delta t to be very tiny. However, the numerical method might need delta t to be so small, like much smaller than you'd expect, just to maintain stability. Because what can happen is a solution may appear to be smooth, but it could have some small, seemingly negligible high-frequency components to it that you might not really see on a plot, for example. But if you don't treat them carefully by choosing a small enough delta t, those high frequency components can explode on you. They can blow up and completely wreck your solution. So it doesn't even make any sense. So this comes about when you are trying to solve systems of DEs where you have components changing, some very slow, some very fast. And so ongoing theme of my research program is, if you're trying to solve differential equations with a high spatial resolution, then you have these, your solutions have low and high frequency components over a wide range of frequencies. And that causes your time step to be forced to be chosen even smaller and smaller. And that's a big problem, because then you're expending a whole lot more computer time than you should have to. And my research program is dedicated to finding ways to get around that. So some of you are going to be involved in those kinds of efforts for your thesis or dissertation.
So the numbers, can we think of, say, I don't know, like e to the x sine x is something.
Yeah.
Like sine x is not changing as much as x is increasing, or t, and the exponential function is increasing a lot, so it gives you the, like you know, as you were saying, that, you know, some variables are increasing a lot. Like, what can be an example of?
Well, the thing is, a lot of times solutions are represented by Fourier series.
Okay.
So you have sine terms of sine or cosine kx, and k ranges from 0 or 1 to who knows what.
Right.
And if you are solving, like if your system of differential equations comes from like a partial differential equation with a fine spatial resolution, the maximum value of k can be so large, so that's at the higher spatial resolution, which computers are always using higher resolution these days. Your maximum k value can be so large, which then forces you to choose a delta t that's even smaller than if you've been solving the same problem at a lower resolution. It just gets, it's a problem that just compounds itself. And so higher resolution means more data, so you're expending more computer time for that reason. Smaller delta t, so you're taking more time steps, so you're expending even more effort. It just mushrooms on you. And when I get to cover stiffness, I'll be able to talk about this more concretely, but it's a big problem, these time-stepping methods. And this is one of the unfortunate things about this particular area of numerical analysis. And that is the basic time-stepping methods that we're going to cover are old, like 100 years old. People do work on time-stepping methods as an active area of research, but when I look at recent research, it's just like tweaks. For instance, can you change the time step adaptively in order to choose it as large as possible and maintain accuracy? So there are a lot of methods that incorporate that, and that helps. But no one has really gone back to revisit how time stepping is done for the kind of problems that we need it for today. And that's something that I'm trying to remedy. Because a lot of times problems are solved a certain way, and people are like, well, it seems okay, what can we do differently? This is how we've always done it, which is a terrible excuse for anything, I might add. Okay, so those are the main issues surrounding numerical methods for ODEs, so the first major part of the course. I was actually expecting to do this overview in just a few minutes and be done with it, but apparently I can ramble a lot. Oh, it doesn't matter. We're still not going to fall behind no matter what I do. Not today, anyway. Okay, now what's the next thing I need? Okay, I'm done with you. Here we go. Okay, so the next major topic area, and this is one that Amber's going to focus on covering, is really one of the most fundamental problems in numerical analysis. So basically, solving AX equals B, where A is an n by n matrix, B is a given n vector that's a right-hand side, and your solution X is also an n vector, that's your unknown. Now, this problem you dealt with in your first linear algebra course. And how did you go about solving it then? What did you use? I know that was a while ago for some of you, or maybe all of you.
What do you mean, like a matrix times a
Yeah.
vector? So you get
Those just
a
solved it
solution
in
to
the last row was.
augment matrix,
Sorry, what?
and then
Yeah, augment the matrix.
matrix, and then you do Gaussian elimination.
Gaussian elimination, yeah. So the first kind of methods we're going to look at is what you saw in your numerical algebra course. The direct methods are what this falls into. Gaussian elimination. And once now Gaussian elimination is not the entire solution process, then you do substitution after that to actually produce the solution. Now, you might think, well, that's something you did by hand in your first linear algebra course, so why do we need to talk about it here? Well, it turns out we do. Because, so there are certain issues that come up that are not when you're solving a small system of equations on paper by hand, but are relevant when you're doing it on a computer, especially for a larger scale system that you could never do by hand. First is conditioning, and that is a problem where you have a small change in either the matrix A or the right-hand side B, and that produces a large change in the solution X. So certain systems are rather numerically unstable that way. And another issue that kind of goes hand in hand with this one is, well, it's an issue for all numerical methods, round-off error. You want to try to prevent a round-off error from getting out of hand. And that leads to what is called pivoting. Now, when you were solving systems by hand in your first linear algebra course, there were different row operations. Mostly you would be adding a multiple of one row to another. You might interchange rows, or you might scale a row. And you would not normally interchange rows very much. You might do it for convenience, or if you had to in order to avoid dividing by zero. That's pretty much the only time you would interchange rows. In numerical methods, we actually interchange rows quite often. And the reason is it's not absolutely necessary, but it helps manage for round-off error, prevent it from mushrooming too much as the computation proceeds, because it's a lot of work, a lot of arithmetic operations being performed, and if you're not careful, that round-off error could really grow. So that's one key difference in the numerical setting versus the analytical setting. So, and that's for direct methods. But another category of methods that would not normally be covered in a regular linear algebra course are iterative methods. Now, iterative methods, you've seen iterative methods last semester for solving nonlinear equations, like Newton's method, secant method, etc. These methods for linear systems share some properties with that. So this is meant for systems of equations that are large and sparse. And by sparse, I mean that most of the entries in your matrix are 0. And those systems are of considerable interest in many applications, like if you're get the system by trying to solve a differential equation. also, what if you have an initial guess? What if you have some idea of what the solution is already? If you're using Gaussian elimination, you have no way of taking advantage of that. Gaussian elimination and substitution doesn't provide any opening to use any information you might have about the solution. So it'd be nice to be able to take advantage of any such information you might have. And there are other reasons too that I'll get into later as to why Gaussian elimination can actually be a terrible idea for many linear systems, and iterative methods are a better choice in terms of minimizing computational expense. And there's different categories of iterative methods we'll look at. Some that are based on fixed point iteration that we saw last semester, and others based on steepest descent. That leads to the well-known conjugate gradient method. Okay, the method is so popular they threw a party for it when it turned 50. I'm not joking. Okay. All right. So this is a part that and we'll be covering mostly. Okay, and then. All right. Then for the final portion of the course, we'll actually be using certain ideas from the rest of the course to solve different kinds of problems. Okay, now, last semester we learned how to solve a single nonlinear equation using Newton's method, bisection, and so forth. Now we'll look at systems of nonlinear equations. And it makes sense that we can cover it at this point because by this time, you'll know how to solve a single nonlinear equation, and you'll know how to solve a system of linear equations. So it's like we're kind of putting the two together. So you're going to find a vector x in Rn, so that some vector valued function of x is equal to the zero vector. So it's root finding in n dimensions. And that could be quite a difficult problem to solve. Using, again, iterative methods. In fact, we're going to take most of the methods that we saw last semester, actually all the methods except for bisection. What's one of the other drawbacks of bisection? We talked last semester about how it's slow. But the other really bad thing about bisection is that it doesn't have a nice analog in higher dimensions, whereas other methods do. So 6 points, iteration, Newton's method, secant method, all can be generalized to a multivariable case. And remember Newton's method, we had to divide by a derivative. What does that mean in n dimensions? You can't divide, instead of a derivative, you have a Jacobian matrix. You can't divide by a matrix. You multiply by the inverse. So we're using these iterative methods, appropriately generalized, and techniques from the part of the course we will have just finished. Because we had, at some various junctures, we had to solve systems of linear equations in order to take a single step for solving a nonlinear equation. So everything we covered here now becomes useful here. Okay. And we won't spend a whole lot of time on this, but it's a nice way to bring certain familiar concepts together. And also how to do this efficiently. It's not really we can do a straightforward generalization of these methods, but that's not necessarily the way to go. We need to do some further tweaking in order to improve efficiency, and some pretty cool things come out of that. And finally, a different sort of differential equation. Instead of initial value problems, we'll look at boundary value problems. So for a boundary value problem, we'll look at what are called 2-point boundary value problems. Something of this form, where your solution is second derivative. So these are the second order differential equations. So you're solving for this function y on some interval ab, and instead of initial conditions, because when you have a second order equation like this in your DE class, like in 285, you would have a condition like this. And what is the other condition that you would normally have for a problem like this? When it was an initial value problem. Because I have a second order equation, so I need two conditions.
Y prime.
Yeah, normally you'd have y prime specified at this initial time a is equal to something, but here we're not going to do that. Instead, this is a boundary value problem, not an initial value problem. So we specify the value of y at the other endpoint, at b. So this is what we've done by 2-point boundary value problem. And we'll look at various techniques for solving it. Interestingly, though, one of the techniques we'll look at is, okay, so we have the shooting method. The shooting method actually redescribes this as an initial value problem. So we actually impose this condition, y prime of a equals something. The trouble is we don't know what the proper slope is supposed to be. So the idea is we guess what the slope should be, and we hope that the solution basically fired from this point hits this point. That's why it's a shooting method, that we're aiming for this. And we have to find a right trajectory, because this is an initial slope. So you're starting at the correct value at this point. So what is the right slope so that when you fire, you hit beta at the other end? And you can structure like an iterative method to try to hit this correctly. So then you're basically falling back on everything we've learned we will have learned earlier for initial value problems. But there are other methods too. You can set up a system of equations using the numerical differentiation schemes that we learned last semester. So that's the method of finite differences. And this could lead to a system of linear or nonlinear equations. If it's a nonlinear system, then we fall back on this stuff. So everything is building on it, on previous things. And then the last method we'll look at is called the Rayleigh-Ritz method, which is a nice introduction, similar to what I do in my research, which deals with spectral methods, where you express the solution y as a linear combination of certain functions, and you try to find a right linear combination to solve this boundary value problem. And there are many ways of doing that, like using Galerkin methods and collocation and so forth. So Rayleigh-Ritz is one that we'll look at just as an example. And the final project largely deals with implementing all of these methods and trying them out in actual problems and seeing how you do. Okay, so this is what you're in for a semester. So quite a bit. Okay. Well, can't imagine there's questions at this point because we haven't really covered anything yet. Now, as before, we'll be working with MATLAB. Now, if you really want to work in another language, I won't stop you. But in MATLAB, so we'll be dealing with in the labs. I wanted to incorporate Python, but I need to build up my own expertise in that first. And I imagine the next time we teach this class, it will be largely about Python instead. Okay. Now, I still have some time left. So, I think in the interest of insulating myself against possibly falling behind later, I can actually do a little bit of material that I had in mind for Monday. Okay. And I'm not sure how far I'll get, that doesn't really matter. Okay. Okay, so I'm just getting to chapter 13 in my notes. There's also chapter 16 in Asher and Greif. Okay. All right, so our IVP, short for initial value problem. I stated this a little while ago. So the general first order differential equation over some interval in time. So we have a well-defined initial time and a final time, which will help us to analyze convergence. And then we have our initial condition. This is our ODE and IC. Okay. Now, so for being able to study convergence of numerical methods, so do they actually, because we're going to be computing solutions with a certain spacing in time, a time step delta t. We'd like to make sure that as delta t goes to 0, your y values that your numerical method produces, which are meant to be approximations of your exact solution at a certain time, actually converges to your exact solution. So we want to make sure that this convergence actually occurs. Okay. All right. I need to phrase this a little more carefully because delta t is going to 0. But we want delta t to go to 0 in such a way that the t value that we're looking at I'll call it t star, which is the initial time plus I delta t is fixed. All right, so the idea is, because what happens is, if delta t is going to 0, but I is remaining fixed, then this t value is just going to go to t naught. But I want to focus on a particular t value and keep it that way. So in other words, as delta t is going to 0, the index I is increasing in order to offset that. So that way, this common t value is stays the same the whole time. And so this is approaching the value of the exact solution at a particular time. And we want this to be true, of course, for all t values in the interval that we're considering. So this is what it means for a numerical solution to converge to the exact solution. All right. And as we go through this chapter, we'll learn various ways of proving that certain methods actually will achieve convergence or not. Okay. Now, I need to say a little something about the underlying initial value problem. We want to make sure that it actually has a solution. So this will give me an opportunity to bring back what I'm sure is one of your favorite concepts from 460. Okay. So a function f depends on t and y satisfies a Lipschitz condition. Remember that? In y, we only care about what's happening in the variable y in this case, not t. On some domain D in R2, if we have the difference between function values where you're evaluating at the same t but different y values. So a change in f with respect to y is bounded by some constant L times the difference in y values. And this is true for any such points in your domain D that you're considering.
L has to be between 0 and 1, right?
It has to be positive, but in this case, right now, just to have a satisfied Lipschitz condition, it doesn't have to be less than 1. Okay, so L is called a Lipschitz constant. Now, I should mention that the consequence of this definition is if your function f is also differentiable, this is the same thing as saying that the partial of f with respect to y is bounded by L. So you can think of L as being a bound-on derivative. But this Lipschitz continuity itself does not require f to have partial derivatives. But if it does, then you have this. So in a sense, it's bounding a rate of change, at least with respect to y. Okay. Now, okay. Now, before we can look at solving this initial value problem numerically, I'd like to make sure that the initial value problem itself has reasonable behavior, because otherwise, if we can't solve a problem analytically, we can't expect to do it numerically either. So if f satisfies this kind of Lipschitz condition, on some domain D, which will be our time interval, Cartesian product with real numbers. So this covers t, and this covers y. Okay. And I need to, and this is a consequence for the Lipschitz that, in fact, if f satisfies Lipschitz condition, it's going to be continuous anyway, but I want to explicitly state that it's continuous. So Lipschitz condition is actually a stronger form of continuity in a way. That a function can be continuous and not satisfy a Lipschitz condition, but not the other way around. And it only satisfies a Lipschitz condition in y. Again, we don't care about how it's behaving with respect to t. Then, the initial value problem on this domain is said to be well posed. Now, actually, for those of you taking 606, I'm going to bring this term up again in that class. What I mean by well posed, there are three conditions. First, the solution has to exist. Second, the solution is unique. And actually, what are these conditions called that I'm stating?
Existence should exist.
So, but these conditions are actually named after somebody.
Huh?
These conditions are actually well posed and are actually named after somebody. No. Hadamard. Yes, these are Hadamard's conditions. Even if you remember who they were named after, or who formulated them, I don't remember what the third condition is supposed to be.
And solution converges to, like.
Give it up. Right. The solution depends continuously on the data.
Yeah, that's better.
You've never heard that one before. So what that means, for instance, is if the initial value only changes a little bit, or maybe the function f changes by a little bit on the domain, that does not cause a large change in the solution. So that way, the problem itself, you can also think of it in numerical terms as being like a well-conditioned problem. And these are the kind of problems we want to apply numerical methods to, because if the problem is not well posed, applying a numerical method is kind of risky. You may get a solution, but it doesn't mean it's the right one. Oddly enough, there are very well-known problems for which that are either known to be ill-posed, or it's not clear if they're well-posed or not, and yet we try numerical methods on them anyway. For instance, there's a well-known equation from image processing that is provably ill-posed, but can be solved numerically anyway. One of the best-known partial differential equations, the Navier-Stokes equations for hydrodynamics, it's not known if they're well posed. I guess people generally believe they are because they're able to produce solutions numerically at least. And in fact, what I've read is that if someone can prove that the Navier-Stokes equations are well posed, they can win a prize of $1 million.
Yeah, like the 3D, the turbulent flow is still up in the air.
Yeah. So if anyone wants to give it a go. All right. Okay, so when studying numerical methods, we're going to assume that our underlying initial value problem at least satisfies this kind of property. Okay, so I have about 10 minutes or so, so I can at least describe the simplest numerical method for solving this kind of initial value problem. And then we'll call it good, and these will be slightly ahead of the game. Okay. So the first category of methods we'll look at, this will spill over into Monday, called one-step methods. And the simplest one of those do a check here. How is this name to be pronounced?
Euler.
Euler, not Euler. That is like fingernails and chalkboard to me. So, in fact, if someone pronounces it the wrong way, I may do fingernails and chalkboard. So that's that annoying. And it was pronounced the wrong way national TV once. I've just never gotten over that. So, yeah, Euler, not Euler. Okay. So first, notation purposes, I'll find my time values, the initial time plus NH. I've used delta T earlier, so a lot of books use delta T, but a lot of other books use H. I'm not really sure why I settled on H, but so this is, actually we used H for other purposes last semester as some sort of spacing. Okay, so these are the times at which we're going to compute our numerical solution. Okay, so what we do is we take a Taylor expansion of your exact solution y of t, and our center is our nth time value. So what we do is our solution at time tn plus 1 would be equal to y at our center, tn. And if I continue the Taylor expansion, we would have h, the difference in time values, times the first derivative at tn. And then I'll just go only to one more term, h squared over 2 y double prime at some unknown point, squiggly, or exceed, that is between tn and tn plus 1. That's all we know about it, but that's okay. So what we do is, to describe Euler's method, we just take this Taylor expansion and we truncate it. We just go ahead and neglect this smallest term here, but it has the h squared, because h is already assumed to be small. So h squared is going to be that much smaller. So when I say y of a certain time, that's in reference to the exact solution. All right, so that's what's going on here. Whereas what I describe here, when I have y with just a subscript, that is in reference to the numerical solution. So yn plus 1 is equal to yn, so these are approximations of each other. And then, well, y prime is equal to f. So I'll fill that in. And f takes two arguments, a t value and a y value. Well, for the y value, I'll just use y sub n. And then this term gets neglected. So this is it. This is how we get our numerical solution. And this is an example of what is called, instead of a differential equation, a difference equation. And the reason for that is, with differential equation, you're looking at dy dt, you have these infinitesimals, dy dt, so infinitely small changes. With a difference equation, you're looking at a finite difference. You have a finite spacing h in time. Here we have yn plus 1 minus yn is a finite difference change in y. So this is a discrete version of a differential equation, like y prime is equal to f of ty, is this difference equation here. And this is the method. This is Euler's method. So that's it. We just use this Taylor expansion only out to, that far. So now, from our initial value, y naught, we can just plug it in here, plug it into f, in order to get y1, and so forth. So the way this goes is, so you're given your initial value y naught, and also your function f of ty. So y1 is y naught plus hf of t naught y naught. And then y1 comes out, and then you use that down here. So y1, and then you plug that into f, and you go with the new value t1 to get y2. And keep in mind, t1 is equal to t naught plus h. So in fact, in between, you can compute your new t values by continually adding h. So then y3 is y2 plus hf of t2 y2, and so on. So this is what your code is doing. It just keeps bumping up the t value, plugging in your latest t value and y value into f, and then the output of that leads you to your new y value. You just keep going. And I will have sample code for Euler's method on the site if it's not posted there already. Okay. So Euler's method is the simplest example of any time-stepping method. Also a one-step method. Also, it's a explicit method because I can just plug and chug it, substituting values into f. I'm not having to actually solve any equation or system of equations here. But later we'll see a slight variation of Euler's method that is implicit, where you do have to do that. Okay. All right. Well, there's not much time left. So I think I'm going to stop here because next is convergence analysis, proving this converges, and that's pretty involved. So I will get into that on Monday. I guess I'll see half of you here during the next hour. Hopefully the recording works.